Okay, let's take a look at the post-activity discussion of investigating basics. So this presentation is going to answer the following questions. What are some of the basic components that make up simple circuits and what do they do? What are the important characteristics of a circuit and how do you measure the different parts? How do you work safely with circuits? How do you measure voltage in a circuit? How does the arrangement of components affect the characteristics of a circuit? And finally, how can I use calculations to design circuits before I create one? Alright, here is a light emitting diode or an LED. So in activity 112, investigating basic circuits, you created a simple circuit similar to that guy. Let me pull up my pen. Alright, so that's what you created. With the circuit active, what happened when you flipped the LED in the opposite direction? When you flipped around the LED did not light up. Okay? What does that tell you? Well, they're a semiconductor and they only work in one direction. Alright, a resistor. What do you think the role of a resistor is? Well, a resistor protects the LED by limiting the flow of current that runs through it. So a resistor is a component made up of material that opposes the flow of the current and therefore has some value of resistance. Again, resistance is anything that opposes the flow of electricity. There's a schematic symbol for a resistor. And there you see the value of the resistor. In this case, it was 330 ohm resistor. Okay? So a resistor kind of opposes the flow of electrical current. So you learned how to use a digital multimeter. So when you switched the leads of a multimeter, it still read the voltage, but the voltage was just negative. So I said that it was important that you make sure that you put the red lead on the positive end and the black lead on the negative end. Alright, you can see in these photos that basically it's going to give you the same value except one will be negative, like in this case. Okay? Alright, how to properly use a digital multimeter? Well, how do you ensure the best precision in reading voltage with the digital multimeters? Well, we're talking about the most significant figures. Alright, so you're going to use a range. The digital multimeter reading becomes more precise by a factor of 10 each time the voltage range is decreased. So the range, alright, if you look here, you'll see that this range right there, alright, 600 volts to 0 volts. Alright, that is a wide range right there. Okay, so the more precise your range becomes, the more precise the reading will become. So between 2 volts and 0 volts, the reading was 1 or plus over. So why was no reading? Well, because the range was too small. It was 4.7 volts, the voltage running through your circuit, but the range was 2 volts. Alright, so that means it was greater than the actual range. So it's not going to give you a reading. So you had to use 20 volts. Okay, hopefully that makes sense. So what is voltage? Well, now that you can measure it, let's see what it is more in detail. But voltage is the electrical force that causes current to flow. It's measured in volts. Okay? This force can be created by separating charges. So a voltage has been described in many different ways as the science around. Let me try that again. Voltage has been described many different ways as the science around electricity has evolved. So we're going to look at voltage more using another component called a capacitor. Alright. A capacitor is an electrical component that stores an electrical charge. Capacitor. So like capacity, all right? A stadium has a capacity, or a restaurant has a total capacity. If a stadium holds 20,000 people, the capacity is 20,000. So a capacitor stores a specific charge. It's basically like a temporary battery. Okay? And capacitors have a positive end and a negative end. And you can see in this picture here, one lead is longer than the other lead. That's very important. So here's an example of a parallel plate capacitor. A battery pushes charge onto the opposite plates, which generates an electrical field. So the positive is going to push it to the negative, and here's that electrical field we're talking about. Alright, so the question is, can you guess which way the test charge would move if this was an electric field? Alright, it's going to move to the left. Okay, so if you had something that would short it out or would touch both ends, in this case like a screwdriver, what would happen? All the charges would move together, and that would basically short it all out. Alright, so that would create a whole bunch of current. And it says here, be careful when dealing with high voltage capacitors. So they're like batteries, so they store electrical charge. So the bigger the capacitor, the bigger the charge. Alright, another source is a battery. A battery is a device that converts chemical energy into electrical energy. The chemical reaction provides more charges for a longer time than a capacitor does. A capacitor will discharge energy and then it needs to be reloaded. A battery has a whole bunch of potential to do work. Alright, and it can do work over a longer period of time. Okay, so what is voltage? Well, in order for a charge to move, there must be a separation of charge or a potential difference across 2 points of a circuit. All right, we'll look at what that means. But voltage is defined mathematically as a change in voltage. It's equal to voltage final minus voltage initial. So what does that mean? Well, let's look at that. Alright, let's say that we had a glass of water. Or a bucket of water. Alright? And it's filled all the way up here. And then I got another bucket of water. And this one's only filled to right here. Okay? And then I have a tube. What's going to happen? Well, water is going to flow from here and it's going to flow into there. And it's going to fill up until both are basically equal. Okay? And that's basically how voltage works. There needs to be a change in voltage in order for it to flow. If there is no change in voltage, if there's no potential difference, then nothing is going to flow. Alright? Hopefully that kind of makes sense to you. Alright. So let's finish this up. So a volt is a joule of work per coulomb of charge. Alright? So 1 volt equals 1 joule of work. So 1 volt equals 1 joule of work per coulomb of charge. So a 12 volt battery is able to produce 12 joules of work for every coulomb a charge can provide. Okay, so both of these situations here, 6A and 6B, they produce 0 volts on the digital multimeter. Why? Well, I know you can see the answer down here, but let's talk about why. There is no separation of charge. What do I mean by that? Well, there's 5 volts coming in, 5 volts coming out. All right? 5 volts minus 5 volts equals what? 0. All right? In order to see the separation or the change in volts, there has to be some sort of difference. In this case, there isn't. Same with this guy. All right? 0 volts minus 0 volts equals 0 volts. So we're looking for a change in voltage. All right, so here's that analogy that I was talking about. Okay? So they kind of beat me to it. But the flow of water from one tank to another is a good analogy for electrical current and the mathematical relationship between voltage, resistance, and currents. All right, so let's take a look. So the difference in water levels, that's your voltage. Okay? The flow of water between the tanks, here's your flow. All right, that's your current. And finally, this valve right here, that is your opposition or your resistance. Okay? So if I were to turn or open this valve, all right, water should flow freely between. If I were to close this valve, now the water would be resisted or opposed against, and now the current isn't going to be as strong. Okay? Hopefully that makes sense. All right, let's take a look at a flashlight. Flashlight is a very simple device, all right, that has few electrical components. All right, so here's a block diagram. That's something you may have designed like in IED, all right, or POE. Very simple black design. We're going to deal with a schematic design. All right, but first look at the black design. You have a D-cell battery here. All right, you have your ground. You have your light bulb. And finally, you have a switch at the top. Schematically, this is all it is. All right, you have a switch, you have a battery, and you have a light bulb. Looking again at the flashlight, okay, when your switch is closed, that means the circuit is closed and the battery and current is flowing freely through the circuit. The light bulb is on, and the light bulb produces some heat. There you go. Now, when the switch is open, current can no longer flow through the light bulb or through the flashlight. Okay? Because it can no longer flow through the flashlight, the light bulb will not turn on. There is no current flowing, and the lamp that's normally has resistance has no it still has resistance, but there's no energy flowing through it. This is resistance. Anything that uses electricity is some sort of resistance. Okay, we're going to look very briefly at current flow. All right, conventional current flow flows from the positive and comes back to the negative. All right. However, it actually flows in reverse, and that is electron flow. We don't really deal with electron flow. All right, we're going to deal with conventional current. Okay, this basically shows exactly what I just talked about, that we're not going to deal with electron flow, that we're only going to deal with conventional current. Okay, Ohm's law. So Ohm's law defines a relationship between voltage, current, and resistance in an electrical circuit. All right, here is, there's a formula for it. Okay, I equals V over R. You probably have seen that in POE. So Ohm's law says current in a resistor varies in direct proportion to the voltage applied to it and is inversely proportional to the resistor's value. Alright, that's a big old fancy saying for this right here. Okay? So I That's your current right there. We measure current in amperes. All right, your V is the potential difference, and that's your volts. And we have looked at the difference in previous slides. And finally, your resistance is measured in ohms. And again, any component, just about any component in an electrical circuit is going to have some sort of resistance. For instance, like a light bulb. Okay? All right, here's Ohm's triangle, and this is a great way to help you remember Ohm's law and help you really figure out either current, resistance, or voltage. And anyways, you can see how the finger, if you don't know what the current is, you can cover up then the I, and you would use V over R to solve. Okay, same thing if you're trying to solve for resistance. Cover up the R, and now you're going to look for V over I. Finally, if you're trying to find the voltage, you're going to go I times R. Alright, so this is a very important slide right here, hence the star. Alright, so here's an example of Ohm's law. So here we go. The flashlight shown uses a 6-volt battery. Alright, that battery is shown right here. It has a bulb with a resistance of 150 ohms. When the flashlight is on, how much current will be drawn from the battery? Alright, so there's your example right there. Right now would be a good opportunity to pause the video and solve the equation. Okay, so if you pause the video and you solve the equation, you should have gotten the answer 40 milliamps. Alright, you may have gotten 0.04 amps, but again, we have to put everything in proper units, so that would be 40 milliamps. Alright, they use Ohm's law, I equals V over R, and we know voltage and we know resistance, so we had to try to find the current. And that you would have found that by 6 over 150. Alright, and there's your answer. Alright, so let's take a look at some circuit configuration here. So while you were building your circuit today, what happened when you removed the LED from the circuits? Well, hopefully you understand that when you remove the LED, now the circuit has an opening in it. Alright? The LED went out. Okay? And you'll see a schematic here in a little bit of why that occurred. But the other LED remained on. Alright, well, why would that be? So here's some circuit configuration here, and you can configure a circuit in two different ways. The first way is a series circuit, okay? And that's when components are connected from end to end. And there's only one path for the electricity or for the current to flow, okay? So that is a series circuit. That's a very simple way to wire up a circuit. If you think of like Christmas lights, used to be when a Christmas light when one light would go off, the entire strand would go off. Well, that was because that it was wired as a series circuit. Well, now that's not necessarily the case. Now they're wired in parallel. Well, what is parallel? Well, parallel is when both ends of the components are connected together, and that allows for multiple paths for the current to flow. So you can see here in this second drawing right here, I'm going to star that up, alright, how the components are all connected together, so it can travel through here, but it can also travel through here, and it can still travel through here. Okay, so this one has several different ways for the current to flow. In the first one over here, there's only one way for it to flow, and as soon as there was an opening in that circuit, everything would turn off. Okay, now each configuration has its uses. Okay, so one isn't better than the other. However, if you're using, if you're dealing with Christmas lights, parallel circuits are the way to go. Okay, we're going to look at Kirchhoff's voltage law, and that's abbreviated KVL. All right, so in the circuit that you created, used a 5-volt power source. All right, the resistor that you used, when you measured it with a multimeter, it should have had about 3 volts running across it. So what did you guess would be the voltage across the LED? Well, Kirchhoff's law basically says that the voltage of all the components should equal the total voltage. In this case, our total voltage is 5 volts. So if we use a multimeter, the voltage across, if you were to add up all the voltage across each component, it should equal 5 volts. So when you measure the voltage across the resistor, as in this the second picture here, let me get a little bit better. Okay, in this second picture right here, you should have had 3 volts. All right. Now, when you measure the voltage across not only the resistor, but the resistor and the LED, it should have equaled 5 volts. All right. 3 volts plus 2 volts equals 5 volts. Hopefully that makes sense. So let's take a look at a series circuit. The current flowing through every series component is equal. All right, that's a very important thing to understand. The current that flows through everything is absolutely equal. The total resistance, all right, is equal to the sum of all the resistances. Well, what does that mean? Well, if you look here, all right, if you were to add up all of that resistance, it should equal the total resistance. We'll take a look at that a little bit later. And the sum of all the voltage drops, in this case, the voltage drop across resistor 1, the voltage drop across 2, and the voltage drop across 3 should equal the total applied voltage, which in this case is 12 volts. Again, that's called Kirchhoff's voltage law. So here is an example. For the series circuit shown below, use the laws of circuit theory to calculate the following. We want to first calculate the total resistance. All right? Think about how you do that. Look back at the previous slide if you need to. The current flowing through each component, so the total current is equal to R1, R2, and R3. Finally, the voltage across each component, so the total voltage is equal to the voltage across resistor 1, across resistor 2, and across resistor 3. Use these results to verify Kirchhoff's voltage law. Alright, so that's what it wants you to do. Go ahead and use Kirchhoff's voltage law to see if all this makes sense. Go ahead and pause the video and do that now. Alright, so the first, finding the total resistance. You should have just added up 220, 470, and 1.2k ohms. Add all that guy up. Should have got 1890, but of course we got to put it in the correct standard units. So 1.89 kilo ohms. Now, current through each component. All right, you're gonna have to use Ohm's law here, and you're looking for current. So you're gonna go voltage over resistance. Voltage total over total resistance. Well, the voltage total is 12. The total resistance we found up here, 1.89. All right, you have to use that K. All right, you have to keep your units the same, and you should have got 6.349 milliamps. All right, this is a series circuit. Your total current is 6.349 milliamps. Hopefully you got that right. You'll get some chances to check that a little bit later. So now, looking at the voltage across each component, all right, again, you're going to use Ohm's law, all right, 6.349, that's your current, times 220 ohms, and you'll get 1.397 volts. That's across this very first resistor, voltage across resistor 1. You'll do this for voltage across 2 and 3. All right, again, taking your total current, 6.349, you're going to multiply it by 470 ohms, and you get 2.984 volts. That's your second guy. Your third guy, 6.349 milliamps times 1.2 kilo ohms equals 7.619. Adding all three of this up, you should get an answer. Go ahead and do that. The answer you should have gotten is 12 volts. And again, this is Kirchhoff's voltage law. The voltage across resistor 1, voltage across resistor 2, voltage across resistor 3. The sum should equal the total voltage, which was 12 volts. We added all this up, you should have got about 12 volts. Now, when you're converting and you're dealing with decimals, sometimes there's going to be a little bit of leeway, and that'll happen, but your answer should be near 12 volts. If you didn't get 12 volts, you need to look at why you didn't get 12 volts. Okay, let's look at Kirchhoff's current law, except this time instead of a series circuit, we'll look at a parallel circuit. So we're really looking at this one right here. Alright, however, on the schematic here, they remove the LEDs and just put in resistors, and it's basically going to be the same thing. It doesn't really make a difference. Alright, also that resistor right here, I know it's very difficult to see, that was also taken out. Okay, so now all we have is two LEDs, but they're just marked as resistors. The question that they're asking, why do you think the 330 resistor placed in the actual circuit when the components are arranged this way? So why did it have a 330 ohm resistor? Okay, that's a question I want you to think about. So for components that are in a series, the current is the same in each component regardless of the resistance value. So the current flowing through the components are going to be the same in a series circuit. But in this one, this is a parallel circuit. Resistors 1 and 2, they're going to have a different current. However, resistor 1 and 2 have something in common, and that is the voltage. In a parallel circuit, the voltage across each component will stay the same. So like we were talking about in a series circuit, Christmas lights, how when one light bulb goes out, they all go out. Well, in a parallel circuit, the voltage is going to remain the same. So even if a light bulb goes out, the voltage across all the other ones will remain the same. Hopefully that makes sense. Alright, let's take a look at some characteristics of a parallel circuit. So the voltage across every parallel component is equal. Again, the voltage is not going to change across a component in a parallel circuit. Now the total resistance is equal to the reciprocal of the sum of the reciprocal. Alright, so think about what that means. So you're going to take the reciprocal of each resistor, add it together, then take the reciprocal of that. Here's a couple ways that shows it. Okay, the sum of all the currents in each branch, so current of resistor 1, a current of resistor 2, and a current of resistor 3, is equal to the total current. This is called Kirchhoff's current law. Alright, so there's a lot of stuff right there. Very important to understand that the voltage across each parallel component is equal. They're all the same. And in order to find the total resistance, you find the reciprocal of the resistor, add it up with all the other reciprocal of the resistors, and then take the reciprocal of that. And again, here's two ways to show that. Finally, the sum of all the currents, that is called Kirchhoff's current law. Okay, so here's an example of a parallel circuit. So use the laws of circuit theory to calculate the following. I want you to calculate the total resistance, the voltage across each component, and the current flowing through each component. And use the results to verify Kirchhoff's current law. So go ahead and do that. Pause the video and go ahead and do that now. Okay, so here's the answer. So the total resistance, again, you're going to take the reciprocal of each the reciprocal of each resistor, add it together with all the other ones, then take the reciprocal of that. So you should have got the total resistance as 346.59 ohms. All right. The voltage across each component should equal 15 volts. All right. So finding the current through each component using Ohm's law, I equals V over R. In this case, R1. All right. So the current over resistor 1 is 31.915 milliamps. The current through resistor 2 is 6.818 milliamps. And the current through resistor 3 is 4.545 milliamps. Add all that up, and your sum of your total current is 43.278 milliamps. So, to verify Kirchhoff's current law, you add up all of that. We already did that, and you saw that the answer is 43.278 milliamps. And we just verified Kirchhoff's current law. So there's two Kirchhoff laws. There's the voltage law, and that says that the sum of all the voltage drops in a series circuit is equal to the total applied voltage. So if you're using a 12-volt battery, all of the voltage drops should equal that 12-volt battery. And the current law. Kirchhoff's current law says that the total current in a parallel circuit equals the sum of each individual branch currents. Alright, now that you know some of the basic characteristics, the components and measurement tools used in electronics, we'll start to build on that knowledge. We're going to look at some scientific and engineering notation, which is not difficult, but it's tricky and it's super important. We're going to be able to identify some analog devices. Remember, analog is the opposite of digital. Finally, we're going to do some hand calculations, some simulation, and some breadboarding to check some of these theory laws that we have learned. So here's a little bit about analog. The circuits we explored to this point have included only analog components. We'll learn about digital components a little bit later on, and they're going to give you specific desired outputs. Also, we're going to look at the random number generator, and the random number generator is an example circuit that we'll use to illustrate all the parts of complete circuit design. It includes both analog stuff and digital stuff.